I will give a talk about interference. So it's been quite a few years I've been working on that. So probably some of you will hear things they have already heard, but I tried to put some recent works and things like that. So I will mainly, I think the main part is about modeling interference. So how to introduce some new statistical model to discuss interference. Just to put a few, so I've got lots of names there because there are different types of works that is present in the in the presentation. Mainly my concern in terms of communication network is about IoT. So IoT, and especially as it was presented a bit before, with a large number of devices, short packets. Sometimes we can have some time constraints also, but not very strict. And of course, one idea is to use some non-orthogonal multiple access. So in that case, you will have some, so that you will have some interference, because even if you have some few devices that are simultaneously active, the set of devices that will be active at the same time will change quite rapidly. And this will induce some interference, which is behaving a little strangely. So that's really what we want to try to capture, and to capture in the full framework. And it's not that easy, as you will see. So the basic, and I will change this hypothesis a little bit later, but the basic is this. So if you look at the transmission, classical transmission, you can have this receipt signal Y there, and you have this interference term, which is the sum over a set of interferers, which is called phi there. Strange I think J or I from the previous talk. So you've got the channel R is the distance between the guy and the receiver. H is your relay fading, whatever you want to put there, and X is your physical layer, so your signal. And this term I will consider it as noise. So if it's changing very quickly, so this could be for two reasons. Either the mobility is high, so the relay fading will change very quickly, and you will have some sort of independence from symbols to symbols or packet to packet. We will see that. Or because the set of interferers is changing very quickly, then you will have what we could call a memoryless linear additive noise channel. That will be a bit provocative there, but that everybody treats as a Gaussian channel. Okay, that's nice, good idea. I will try to show you why we should perhaps think of something else. So I know I take some risks there. There are many people from coding that knows that much better than me. So when you see that, what you see, oh, you should not see the small line. Sorry, I forgot this one. I didn't see it on my computer. So just look at the blue line. You see SNR. I didn't put the scales just to give you some that you guess. And you've got beta array, classical. So what you ask there is, what type of coding are you using? So this is BPSK, it's very quick computer simulation. I use a block turbo code because it's already implemented on MATLAB, and I did no effort to do that. And it takes LLR as input, so it's exactly what I wanted. And it's a Gaussian noise, so perfect. Then I show you this. What is your guess? What has changed? Could be fading. It's not. It's still an additive Gaussian noise channel. It's not the coding, it's not the modulation, it's nothing like that. Correlation phase? No. It's just the statistical property of the noise. I go from a Gaussian noise to an epsilon contaminated noise. So it's a mixture of two Gaussian noise, one with a small variance on the probability of appearance, which is quite high. It's 0.9 in my case. And another one which sometimes appears with a lower probability, but a higher variance. So it gives what? It gives that, if you want to see it. So the first on the top is the Gaussian noise, which gives the blue curve, and the other one are three different realizations which depend on the sigma 1 and sigma 2, the two variants of the components. And you can analyze that as you want. So it's sort of impulsive noise. I call it impulsive noise. And with the same SNR, you have completely different values. And if you go one step further, so what you would do probably, or what your hardware part of your receiver would do, it would do some threshold. So it would clip the high values. That's what you have with the two dotted green curves. So the green is one of the three cases. I think the one in the middle I choose. And if you do some what I call soft limiters there, so you clip your signal, you've got the performance, so you've got an increase in performance. It's still completely different from the Gaussian noise, but it is. And I put the last one there, optimal. Where is the optimal receiver? It's here, but there's no error, so you don't see it. So it means with the same SNR, you can go from this blue curve there to something where you don't have any error at any SNR, because the variance of the main component is very small. When you have a large component, the Gaussian receiver, or the LLR you calculate with the Gaussian, is completely full. When if you take it a little bit more intelligently, it's not. So my point there is just to say, okay, perhaps we should. So my interpretation of what people do in telecommunication now, they try to go to the blue model. They do everything to go to the Gaussian case. And anyway, even if they don't do it, they do it because in their optimization problem, it's the way you optimize the system. You use the Shannon capacity, usually the one in the Gaussian channel, or you use stuff like this. So you always assume this Gaussian case. I will say that, and I will not give you a good answer at the end because I don't know if it's a good way to proceed or not. Perhaps it is, but I don't find the answer. Okay. So the question I will try to address today is how to model this noise. We have it. We have it, especially if you are in a large system with a constraint in delay. You cannot coordinate everything. You can perhaps doing in a mobile networks with phones, but when it comes to IoT with low-cost devices, I would not recommend to go for that, even if I think that's what they try to do with 5G, but I think it's not a good idea. So how can we model it? Can we show this behavior in measurements? So I will take a little time to discuss that if I have. And then I will present you some results about capacity. So we can, if the model I propose is good, we can try to have some results on capacity, and we can discuss that. And then if I got time, but I'm not sure I will have, I can show you what you can do in the receiver design. We try to check the time. Not too fast. So how to model interference? So first, I think I will go quickly on this. I don't know, you are all aware of what interference is. So interference is a collection of all the signals you received from the others, so unwanted signals. Of course, you can do some very sophisticated signal processing and try to do some multi-user approach and stuff. I don't do that. It's noise. It's noise, and it could be noise simply because it comes from another system. You know, you've got a LoRa communications, and it comes from Sigfox. You are not going to decode the Sigfox signals. So it could be that. And then, okay, you can write it like this. I already talked about this equation. I try to keep the same notation all the time, but I hope it will not change. What are the statistical properties of this? That's the question. So the reflex is to say, okay, we've got a sum. A large sum, because there are many users. central limit theorem, Gaussian. Good. So there are two things I can say. I've got nothing to say against that. So if you are stick on that, I will not be able to fight because you're right. But if this number of users is not so big, and especially if the number of strong users, of the guys which are close to you and which are really the ones that makes trouble, is not so high, then the time that your central limit is, your convergence is going to be done is very long. You need a very, very large number of users, and this will not work. And then I will show you that if you assume, and again, you can tell me you're going in a very bad way and you should not do that. But you know, you've got this term, I don't have a laser there, which is R at the distance minus eta/2. Don't know, so it's a channel attenuation if you want in amplitude. So if R goes to 0, so the guy is coming very close to you, then this term goes to infinity. So of course, you should not do that. You should have a better model than this that takes near field into account, or that threshold, or you have a guard zone around. But if you do that, you've got this term that goes to, when R goes to 0, this goes to infinity. And when this happens, your condition on the central limit theorem does not hold because you have a finite variance condition on this. So you have to go to the generalized central limit theorem, which exists. And I don't know if you know the results, but you will know it soon. That's teasing a little bit. Okay, so many people have noticed that the Gaussian assumption is not good in many cases, and there has been a lot of work around this. The first one, I think, the first significant one, at least in our community, are from Middleton. So it's 50 years ago or something like that. So it's quite old. But this one is interesting. It's already based on stochastic.
A stupid question to understand. So here there is no time. So you're just discussing one short variable.
For now, yes. For now, I will increase the dimensions a bit later. So Middleton start from a Poisson point process also. So that's a link with more recent models. Then you've got a lot of approaches that say, okay, I see that. I try to find empirically, I try to fit the distribution, and then I see if my receiver works better. That's globally how they do. And you've got a lot of proposals where you can have some Gaussian mixture, generalized Gaussian Laplace. You've got many distributions you can find in the literature. And I prefer the alpha stable case because I will show you, but it has been used. It's not, it's an old story also. So again, the one shot, the scalar case for now. If you consider that you have your interferers that are arranged according to an homogeneous Poisson point process, and if you have exactly the model I presented you a bit before, which is there, I equal to this equation there, then you can show, and it's you have the long way and you have the short way, you can show that I is an isotropic, so in the complex case, is an isotropic alpha stable random variable, and you can calculate the alpha, which only depends on the eta there, which is my channel attenuation coefficient. So it really only depends on that. So it's a bit surprising, but it is. And you've got another parameter for your stable distribution, which is the dispersion, a bit like the variance in the Gaussian case. And you can express this as your globally your system parameters. Like you see that, I will not detail, but you find lambda, which is the density of users. You find again the channel attenuation coefficient, and you find even the fading, so H, which is there, and the signaling you have for your source, which is X. So that's quite interesting. The proof, so the short proof is very quick. if you look at books, you try to find the Lepage series representation. So you start with your expression of the interference up there. And then because of the homogeneous Poisson point process assumption for your location of users, the R can be mapped to a 1D Poisson point process with the given intensity there. And this is exactly a Lepage representation of an alpha stable random variable. So that's it. If you prefer, if you want to spend more time, you can calculate the characteristic function. and it works also, but I did my mathematician colleagues to do that personally. Just to show for those who prefer pictures and equations. So this is on the left an alpha stable case. On the right, this is a Gaussian distribution. So sometimes you go to conference and people show you some distribution and they fit a Gaussian. They don't make any test and they say, okay, it's good. It fits. It looks like it's the same. Especially when you do people doing, don't want to say it bad on everybody, but you know, do some channel models and stuff. They just fit visually. But you have to look into the details. You have to look to the tails. So you have to be a bit careful when you try to check if your interference is Gaussian or not, because it's in the tails that you are going to see the fact that it's not. And this is sometimes a bit more complicated to see. I really think it's really important nowadays, because if I refer to Jean-Marie's talk or previous talks, we want to have some reliability with probability of error of 10 minus 9, you said, I think, something like that. So if you neglect the tail, it will work, theoretically speaking, because the 0.00001 will come from this event that you do not predict with a Gaussian distribution or something else. Okay, that's another way. Just one comment, because so here we have a complex random variable, which is isotropic. And contrarily to the Gaussian case, when it's isotropic, it's not independent. So your real and imaginary part are not independent. If it was independent, so this would, I'm not sure I put a good picture, but it would look like something like this. Again, you could say, okay, it's but if you project it on a 2D plan, then you've got this representation. So this is the real part, for instance, and this is the imaginary part on the other axis. And you don't have something which is isotropic. It's rare to have a big value. It's very, very rare to have two big values at the same time if it's independent. So if you want something isotropic, it means you've got a dependent structure into your own.
What does isotropic mean?
Isotropic means, so it's the same properties in all directions.
Yes,
it's
here it said it is isotropic.
So if it is isotropic, it means it is dependent. It is not independent. But to plot it, so it means your real and imaginary part are not independent. It's not like the Gaussian case. So the Gaussian case is always a bit specific. If it's isotropic, it means real and
means for complex number.
Yes.
Both phase.
Yeah.
Okay. Not necessarily related to that.
No, it's a complex case there.
Yes, it's not related to the isotropic with a special.
Not related to the position of no. Okay, sorry if there was a confusion. It's really on my random variable signal. The signal, yes.
Do you have somehow some synchronization, because it's completely random? We may imagine that the system is rotating and then you don't observe this kind of.
It should be. It's the theory tells you it's isotropic. What I just mentioned here, so I should see how I do my remark better, is that because it's isotropic, it's dependent. You've got a dependence between the real and the imaginary part. You cannot draw two random stable random variables and make your interference. That's what it means. Independently, you have to make. There are tools to do that. Okay, so just to go a little bit quick into the results. Here I show some validation of the model. It's always a bit tricky to validate statistical model, I think. But we used to do that the cool black light blur divergence. I will not repeat it too many times. In fact, we simulate a system completely independently. So we used, in that case, an homogeneous Poisson process. We did it with other processes. We derive the parameters of our models, and then we compare a realization of the simulated environment to a realization of the model. Completely realized independently, except the parameter. And what you see there is the fit. So the lower the divergence, the better the fit of 3 models. So the theoretical stable is the one which comes from homogeneous Poisson process. So you calculate theoretically the parameters. You just know the parameters of your channels and the parameters of your Poisson point process that defines the position of users. You calculate the parameters of and you have this blue curve. What this blue curve tells you is that in the x-axis, you've got the guard zone, because the first thing that people tell me, of course, you've got no guard zone. So you've got this infinite power, which is physically not feasible. Correct. But what it tells you is if you make these assumptions, the model is very good. But what you see is that this theoretical model is rapidly bad. I agree with you. On the right, the orange line is the Gaussian model. So you see that the Gaussian model, if you really increase your guard zone, so you forbid anybody to speak around you on a large area, then it tends to be Gaussian, because you suppress these strong guys that makes your system not Gaussian. And the thing is that when you reduce this guard zone, then the model does not fit anymore.
So we are calculating KL of a stable random variable with respect to a Gaussian?
No, the model, so it can be a Gaussian in the right case, it can be a stable in the, so this is the model, and between that and simulated data. And the red one is a stable model, but we have fitted the parameters. So we realize a simulation, we estimate the parameter of the stable model, and then we compare with another realization of the model and the step. And the thing is that we see that this, so on the right side, you've got the alpha parameter of your model. So if you're not familiar with alpha stable, alpha goes between 0 and 2. The smaller it is, the more impulsive it is. And when it goes to 2, it's Gaussian. And you see that your alpha is going from 0.8, which is a theoretical value due to the parameters we choose for the channel, to 2, and it tends to 2. So it goes from a purely stable, the true model we have, to Gaussian, going through some different stable state, let's call it, with different alpha. And if you do that, you've got a model that, an alpha stable model that fits quite well for the full range, because the Gaussian is included in the Gaussian, in the stable distributions.
How did you fit the stable? There's not even a closed form for the PDFs.
Yes, but there are tools to. There are a long history of estimation of parameters for stable distribution. So to be fully honest, I can remember Kutrovelis and the way they do it. I have to check exactly the method. But now there is a MATLAB function, you just have stable fit to make it. But there are, no, I'm joking a little bit, but there are methods that are really well known to estimate the parameter. They don't work in every range very well, but in that case, we've got lots of that. We can generate lots of data. We are in a range where it's not so difficult to estimate, so it works well.
And then regarding the KL, the KL divergence is not symmetric. So is it important if you don't the opposite arrangement of variables? because so the fact that we have the infinity part at the beginning, it has to do with the asymmetry of the KL, right?
With the fact that it's
Well, my statement is that if we plot the other way around the KL, we will get something else. So what is?
perhaps we will have different values. I've got to check that, but I think we will have the same conclusion. The conclusions are very logical there.
Okay.
So that's perhaps why I didn't.
Okay.
You should not believe something because you want to believe it. I know, but that's exactly what I expect. You know, I know that I'm Gaussian in that case, and the Gaussian fits well. I know that I'm alpha stable in that case, it fits well. So just to be sure that I'm not confused by what I'm doing. Of course, the guard zone and the infinite network. Yes, if you have guard zone and if you have a finite, so there are many works on this. It's not alpha stable. You have different statistics. You've got infinite series. I think the Rockwell Middleton started from that. And in stochastic geometry, you have many very nice papers around this. So you've got very nice expressions. It's just a little bit complicated to handle usually when you really want to do a receiver or to do something practical. And of course, we are aware that the stable works because of this R tends to 0, which makes power infinite, which of course is not true. What I can tell you is that it's better to have, it's a better model than the Gaussian one. So it's perhaps not the exact one, but it's a better one, and we can do something with it. So a model is not exactly the representation of the truth. Like I was talking this morning, like a white noise. Noise is white only where we are looking at it. It's not really white, in fact. But you are very used with white Gaussian noise, and you are very happy with this model. So you could be happy with stable. Okay, so just getting, because I think time is passing. It's supposed to finish 45, yes. Let's make things a bit more complex. So let's go into a vector case. So I try to represent here the reason why we introduce a vector model. It's not time really. It's you are a user and you are using several resource blocks, like was discussed a little bit in the previous section. And you randomly select these resource blocks, and everybody does the same. So in the analytical approach we have a very simple method. We have, let's say, n resource blocks, and you select the resource blocks you are going to use with probability p. So your p is something related to the quantity of information you want to transmit. But okay, it makes things a bit tractable. And then what is happening is that if you look at different, for instance, subbands there, if it's frequency and you define and you choose your different subbands where you are going to transmit, you will have different set of interferers on each subband where you are going to transmit. If these interferers are interferer sets are completely disjoint, then it's independent, it's fine. If they are not, then you have some dependence. If they are exactly the same, it's a specific dependence. I'm going to say a word about this. And we want to model this. Okay, so just said a bit differently. So we have a realization of my interference there, which depends on the set of interferer which is seen at this time. And if at the next time the set is different, then something is going to change. But if it's not fully different, you have dependence. So of course, when we talk about dependence, we would like to use the correlations. It's like we use, but when you work with alpha stable, you've got a problem because of infinite second order moments. You cannot use correlation. So we want something that has to be adapted to alpha stable and that can capture this, I told you when you've got a large value on one dimension, you've got a probability which is not negligible that you have got another large value on the second dimension. And this is not captured by correlation. And what we could do, of course, is to use multivariate alpha stable. So I let that for mathematicians. I've seen very nice discussions about this, but it's very tricky to handle. So we don't do that. Our idea is to separate a little bit the dependent structure to the marginals behavior I just described before, using the copula theory. So this is a very nice theory. I don't know if you've been across, but probably. So you can express your cumulative distribution there like a function, which is your copula, of the marginals cumulative distribution. And this is very nice because it separates the copula, which captures the dependence, and the marginals.
Why
So-
not the joint Fourier or in the joint Laplace or equivalent joint characteristic function?
Of the stable.
Yeah.
Because it's really difficult to generate. We found it, I found it very difficult to handle simply because going in high dimension in for generating samples, for trying to write down the equation, it would probably be better, but it's a question of and the other point also is that the copula can be applied to any types of marginals. So if you are not at ease with alpha stable, you could say, okay, it's Middleton, or it's and you can still use the framework of copulas to model the dependence. So we do that. So we have to select. So just to go quickly, I don't remember where I am. So the T copula is there. I'm a bit further. So if you have the copula, you can express the PDF, which is expressed like that. So again, you separate the dependent components to the independent one. And of course, we have many questions behind it. What is a good copula? You've got lots of copula. So you have good ones. Clara told us there is one, which is good. It's unique and it exists. You've got this proven, which is quite important. But okay, it's quite difficult to know which one is a good one. And if you can have one which is parametric, you can make calculation with it, it's better. And parametric, and you need to be able to estimate the parameters, of course. Which shows the T copula. I will not go. We tried others, but I think this one are quite good for the questions we have. So the heavy tail. So in the end, we've got this T copula alpha stable model. So T copula for the dependence, alpha stable for the marginals, to capture the heavy tail behavior, alpha stable, and then the dependence through the copula. And in the end, our model only depends on 4 parameters, because we've got symmetric alpha stable. Stable is 4 parameters normally, but only 2. So it's a student T. It's based on the student T. Yes, I think I've got the equation. No, I didn't put them, so I can. It's based on student T, so it's non-distribution. So yes, it's a T distribution there. So F mu is a T distribution and multivariate and univariate. We've got analytical expression for this. It's quite easy to work with it. Okay, I try to. Yeah, I will have to close. So we've got 3 types of model. When the phi, so the set of interference independent from one is constant, sorry. We've got a case which is fully dependent components in your vector. It's very interesting because it's what we call the sub-Gaussian case. It's a specific case of alpha stable distribution. So it means you've got one packet, if you see, you've got one packet, and you've got a Gaussian vector on it. And then you've got another packet, you've got still a Gaussian vector, but with a different variance. And the other extreme case would be the independent on the different cases. So we, again, did some model validity. It works well. I will not detail because time has been too long before. We've got problems. For instance, we've got a dependent structure which is not the same between the real and imaginary part on the same band and between two different bands. And I think this is not captured by our model. And we should do something this. Okay, we've measured it. So just to tell you if you want to see the paper, but we have been doing measurements in Aalborg, and it has been shown that the tail of the distribution is not exponential, it's really sub-exponential, so it fits quite well with stable. Okay, I will not put my hand there to say it is, but it fits well. And just to show you one thing and to put that in the, I just want to show this one. So we've been working with capacity with stable distribution, except in that case, we need to change the conditions because we have an infinite variance. So if we want to show this result, we need to suppress this, to relax a little bit this assumption. But you see, we have a lower bound which looks like that, because stable distribution have very similar property to Gaussian distribution. And in particular, you've got a scaling property, so you can use that. You can say that if X is stable and N is stable, then Y is stable. So that's what you use when you want to. And you can also have the sum, the dispersion, so of a sum of two stable random variables. So you can show this result, which is interesting because it looks like what you are used to use, but with one parameter in addition, which is alpha, which is your impulsiveness. So perhaps we should think about adding impulsiveness in the equations. And I will stop there. Sorry for this. I've been too long. And anyway, my conclusions are not very interesting because you know you do it really at the end when it's a bit late. And you say, okay, we'll see. So if you have any questions, because we've done some work a little bit on the capacity, we've got many issues to solve. We know how to make a good receiver. So we didn't take really into account the dependent structures up to now, but as long as it's independent Gaussians, we know how to make very efficient receivers. Even with short packets, we've tried with short packets and with unsupervised approach. It means we don't need to know a priori what is the distribution of your interference. It works if it's Middleton, if it's stable, if it's Gaussian, if it's whatever. You just have an estimation step before, and you just don't do a simple LLR like you are used to. Thank you very much.